Hey there, physics folks. Today we want to derive the formula for the period of a simple pendulum. Now, if you recall, we already did an investigation in class of what parameters might affect the period of the pendulum, and we determined after trying amplitude, mass, all kinds of different parameters, that the length and the gravitational acceleration were the only two factors that seemed to affect the period of the pendulum. We further, or more specifically, found that the period of the pendulum depended directly or somewhat directly on the length, and indirectly or inversely with the acceleration due to gravity. That is, as the length became bigger, the period became bigger. And we surmised that if the acceleration due to gravity were bigger, it would accelerate faster back to equilibrium so that the period would become slower. Now, when we analyzed the units, we looked at a dimensional analysis, and we learned that this relationship, this proportionality, could be more appropriate if we took the square root of L over G, because that meant that the period would come out in seconds. And then finally, we told you that the period of the pendulum is t equals 2 pi root L over G, but we never told you where the 2 pi came from. So we'll go ahead and take a look at that today. Again, the simple pendulum, as it moves back and forth, turns out that as it moves through its motion, and if the angle of displacement is small, that it will exhibit simple harmonic motion. So, simple harmonic motion, of course, is the topic that we've been discussing for the last week or so, and we've derived all of these formulas due to simple harmonic motion, except for the period of the pendulum. So let's do that today. So the first thing we want to do is identify a few things about the pendulum. So first of all, we've got a pendulum is nothing more than a mass on the end of a string that has been displaced from its equilibrium position by a certain amount, and it swings to and fro through some arc length in some form of circular motion. Now, if we can label this angle theta. We of course know this is the length of the pendulum. Because we're talking about simple harmonic motion and displacement from equilibrium, we know that we can define the displacement from equilibrium as x, so that's how far it's been displaced, and as the pendulum swings, it will move through a circular arc that we might call S. Okay? Now, of course, if this pendulum is going to swing back to its happy place, back to equilibrium, and then continue along its path, we know that there must be a force pulling it back. Well, where does that force come from? Well, let's start with a free body diagram. We know that, of course, the tension, the string is attached to it. There must be a tension force upward. Now, interestingly, the tension force up on the string provides no change in the motion because, of course, it's perpendicular to the motion of the ball or the bob at any given time. Furthermore, it provides no torque for this rotational motion because, of course, the tension, the force, acts through the axis of rotation. So there must be another force that's responsible for this motion, and of course, we've alluded to it already. It's the force due to gravity. We call the weight force, or mg, and we can say that we know that weight force always acts towards the center of the Earth, but because it's on a string, we know that there's a component of that force that acts in the direction of motion of the pendulum. Now, if we just do a little bit of geometry here, extend the tension line down here, we can see that this is theta as well, so these thetas are the same, and we know that this is sort of the opposite side to that angle theta, so we can label this force that's pulling it back towards home, or accelerating it home, is mg sine theta. Okay? Now, I'm going to go a step further and say that because x is moving in the positive direction, we're moving it away from equilibrium in the positive direction, then that mg sine theta must be pulling it back towards equilibrium, so that's got to be in the negative direction. Now, where do we go from here? Well, where we often go is that the sum of the forces equals the mass times the acceleration. Now, if we look carefully, the only force that acts on this pendulum bob to cause motion in the direction that the pendulum can move, meaning back to its equilibrium spot, is the mg sine theta force. So I'm going to put in here negative mg sine theta equals ma. Now again, the reason it's negative is because it is accelerating back from where it was displaced. And if we choose to the right as positive, then back towards its happy place is in the negative direction, or the opposite direction, if you will. That's all you have to really remember. Now, you can see, as many times before, the m's cancel, so we can get rid of the m's, and we now have an expression that says, and I'm just going to flip this around so we can see it, a is equal to negative g sine theta. Okay? Now, here's the next step that comes up oftentimes when we have angles and rotation and arc length, and it turns out that I'm going to tell you that for small angles, and how small we'll see in just a minute, for small angles, we can say that sine theta is equal to theta. What? Well, that's if we measure this in radians, that is going to be true for small angles. Now, how small? Well, let's take a look. So what I've done here is I've simply created a table of different angles. So I go from degrees 0 by 0.5s up to 10, and I've changed those degrees to radians. You can see that when we have 15 degrees, that's about pi over 12, and you can figure that out. The arc length s is simply what we're measuring here, and the x, or sine of theta, is the straight line path. So let's just make sure we can see this. So we have the x, which is the displacement of equilibrium. That's this number. Okay? And we have the arc length s. And what I'm suggesting is that for small angles, the arc length, which is the theta in radians, is equal to the straight line distance for very small angles. Now, of course, it's not exactly equal, but let's see how close it is. So if you come down here and let's say 5 degrees. Well, the difference between the arc length and the straight line path, or the sine of theta, so the difference between theta in arc and theta, sine theta, is 1 part in 10,000. So it's a very, very small difference. Even if we go up to 10 degrees, you can see that difference is only it's close to it's 0.9 parts in 10,000. So effectively, for small angles, it is true that theta equals sine theta. Okay, so just trust me on that, and then you can look up the numbers if you wish. Now, if that's true, then I know that x equals s. So I can say that s equals x. So in other words, basically the straight line path is effectively the same length as the arc length path if the angles are small. And you can see anything below 10 degrees is 1 part in 10,000 or smaller difference. So what can we say now? Well, we can simply say that acceleration, again, is not g sine theta, but acceleration is just negative g times theta. Okay? Now we know the definition of theta in radians is equal to s over r, and we know that if s equals x and r equals l, because that's the radius of the rotation, we can therefore say that theta equals equals x over L. Okay? Because S over R is the same as x over L, and so now we can get this expression in acceleration in terms of everything that we have here, which would be acceleration is equal to negative g times x over L. And I'm going to put that in a little box because that's as far as we can go with F equals ma and looking at arc length. Okay, so now let's shift back to simple harmonic motion, because if arc length is small, if angles are small, we know that it's going to behave according to simple harmonic motion. So we've developed an expression for A here. Let's see if we have an expression for A here, and of course we do. So A equals negative A omega, where A is the amplitude, omega is the angular speed squared, times cosine omega t. Okay, so I'm going to go ahead and write that down, and I can say, I can write A equals negative A, the amplitude, omega squared, cosine omega t. Okay? Now, when we've displaced this distance, when the displacement from equilibrium, so at x equals a, meaning we've got it to the full amplitude, we know that cosine omega t equals 1. So we can basically just eliminate that and say that a equals negative a omega squared. Okay? And that, of course, is also the expression for the maximum acceleration, and the maximum acceleration for the pendulum occurs when it has its greatest displacement from equilibrium. Now, interestingly enough, a is the amplitude or the displacement from equilibrium. So we can say a equals x, and we know from definition that omega is the rate, the angular frequency, how often it goes through one cycle. So that's 2 pi radians, which is one cycle, divided by the period of that motion. And so now we can substitute omega for 2 pi over t, and we can substitute x for a. So now we can take this expression and say a is equal to negative x times the square of 2 pi over t. And I think what you can probably see right now is we've gone as far as we can in terms of what we know about this motion for simple harmonic motion. Here we have our expression from Newton's second law. We can now combine these two and set them equal to each other, because we know, of course, they are the same acceleration, and we can say if the first term we came up with, or expression we came with, was negative g times x over L is equal to negative x times the quantity 2 pi over t, period, squared. And again, I think you can see some interesting things happening here. We see that the negative signs go away. We can also see that the x, meaning the amplitude, goes away, and we found, certainly in our investigation, that the amplitude of a pendulum didn't affect the period. And so now we are left with an expression that says g over L equals the quantity 2 pi over t all squared. When we want to solve for t, because that's our goal today, we're going to square root both sides and rearrange, and you will see that t is equal to 2 pi root L over g. And there we have the formula for the period of a pendulum, based on Newton's second law and the idea of simple harmonic motion. That's all for today. Feel free to watch this video again, ask any questions you have in class. I'll post this as a link in the video, and thanks for watching.